Interactions of molecules in a nutshell. So what is this exactly? So when you have different compounds or different elements inside of a location, they interact with each other. And these interactions are known as intermolecular force. Intermolecular means between two molecules because the word inter means between. This not to be confused with covalent, metallic, and ionic bonding, which are known as intramolecular. That's within a compound. That's what holds the compound together. This force does not hold a compound together. These are forces between two different compounds or two different elements. So they are between, not within. And that makes them a little bit weaker, actually significantly weaker than ionic, covalent, and metallic bonding. So you want to keep that in mind when you're thinking of these particular types of interactions. So what happens when you add molecules to water? So let's start with the water analysis, since that's the easiest way to kind of relate to things you're familiar with. So things with dipole and hydrogen bonding force dissolve in water. So those are two of the known forces, and we'll go into what each of those are. But things that have dipole and Nondispersion, dipole and hydrogen bonding will dissolve in water, and that's because water has dipole and hydrogen bonding. So the takeaway from that little piece of information is that things that have similar characteristics, similar IMFs, which we're going to refer to intermolecular forces as, will have an ability to mix with each other. So if you've ever put something in water and it mixed with it, that means it's able to have one of those properties. Same sense, if you put oil in water, they don't mix. So why is that? So that tells you that oil does not have hydrogen bonding, it doesn't have dipole. So that's why the interaction doesn't happen. So you can determine a lot based on something's interaction with water. So intermolecular force, once again, these are forces between compounds. So this is what intermolecular force is right here. You can see it's between the two compounds. This not to be confused with intramolecular, which is the covalent bond holding this compound together. Intermolecular is just a force between this compound and this compound. So if you have HCl solution, these forces are all over the place inside that solution because there's a whole bunch of these molecules. You remember, when you have a solution or quantity of something, it's not just one or two of them, it's a whole bunch. These are working in intermolecular forces, like we mentioned earlier. And there are four types, and here's the hierarchy. The strongest is ion-dipole interactions. These are between ions and water. So, for example, you add Na8 plus to water, and we'll add NaCl. So this is an ionic compound. This is the cation, this is the anion. But when you have NaCl, it just looks like this, right? Just a compound together. So what happens with water, it surrounds the NaCl molecule. So how does it surround it? Well, water, as we mentioned, was polar, right? So here is what's referred to as the positive end. And this is what we call the negative end. Dipole just means an unequal distribution of electrons. It's because one element likes electrons more than the other, the molecule becomes polar. It's just an unequal relationship between the substances involved. So in the case of water, it has what's called these positive ends on the H's and the negative on the O, and you're wondering, why is that happening? Well, if you remember electronegativity, you should know that O is more electronegative than H. So it has more pull of electrons toward itself than the H does. So that's what creates this distribution of electrons. The electrons want to hang out with the O more because it's more electronegative. So in any case, the way the water is going to surround itself is going to take its positive ends and surround the anion, because anions are negative. And what you want to always remember is opposites attract. In the same sense, its O end, which is the negative end, is going to attract itself to this end. Now, why does it do that? The reason it does is because this is able to attract and pull this. The H's are able to pull and attract the Cl, and now you have dissolving occurring. That attraction between this O and this Na and then this H and the Cl is referred to as ion dipole. That's what ion dipole means. It's an ion attraction to a polar molecule. Now, the most common polar molecule you're going to deal with is water. So for our purposes right now, you could just assume ions interaction with water is called an ion dipole, and it's the strongest out of all the forces we're going to be talking about. Number two is hydrogen bonding. It's found when H is bonded to F, O, or N, the fun elements. So H likes the fun elements. What does that mean? That means if I have HF, hydrogen bonding. If I have NH3, hydrogen bonding. If I have H2O, hydrogen bonding. Why? Because in each of these situations, H is attached to either F, N, or O. If I have CH4, no hydrogen bonding. If I have, HI, no hydrogen bonding. Why? these do not involve the fun elements. So it's got to be one of these three. It's got to be H attached to one of these three to have hydrogen bonding. This is the second strongest intermolecular force. Number 3 on our list, sorry, went a little too fast there. Number 3 on our list is dipole-dipole, and these are for polar molecules. So anytime the molecule is polar, you have dipole-dipole interactions. And if you forgot what polar means or are not familiar with it, we're going to go into it in a few minutes. And then finally, London dispersion forces. Everything has London dispersion forces. H2O, HF, H2O, all the molecules I just drew have London dispersion forces. So everything has it. It's always there. The only question is the strongest force available? And if it is, we got to look at it more carefully. If it isn't, we just make note that it exists there, and then we move on to the other forces that are stronger, one of the three that are above it. So let's first talk about hydrogen bonding. You can see hydrogen bonding, basically the way it works is between the H of one of the fun molecules, right, with the lone pair of the other. That's how you have hydrogen bonding, between the H and the lone pair. So if anybody ever asks you what's the definition of hydrogen bonding, you just say it's between the H of one molecule bond to F(O)N with a lone pair of another molecule bond to F(O)N. Now, you can't have hydrogen bonding. Let's say we did CH4 for fun of it. We know CH4 doesn't have hydrogen bonding, right? So you can't just assume because there's an H here that this can happen. No, 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 no. Both of these molecules must have either F, O, or N. So if I did an H3, like this, then yeah, you get a hydrogen bonding between here and those lone pairs. That's fine, because both of these have F, O, or N. That's the requirement for hydrogen bonding, so remember that. If they don't both have it, there's no hydrogen bonding. Here's another example. You have HF over here. You can see hydrogen bonding between the F and the H. You see the H2O again. Key feature, once again, both molecules must have HF or, must have FO or N in order to have it. All right, polarity. Remember, polarity is basically an equal sharing of electrons because the two elements involved don't have similar electronegativities. So in the case of HH, they both have the same electronegativity, so we refer to it as nonpolar. Why? The distribution is equal. So if it's equal distribution of electrons, we say it's nonpolar. Same thing with F2. Why? Both Fs have the same electronegativity. There's no difference between them. There has to be a difference between the two nonmetals to have a polar molecule. HF, now you can see there's a difference of electronegativity. And the way we show electronegativity, the difference in it, we use an arrow to point to whatever's more electronegative, which is the F. And we use these funny looking D symbols. Looks something like this. It's called the delta or dipole symbol. And what it shows is what the positive end and the negative end of that polar molecule is. So whatever is more electronegative is going to have the negative dipole. Whatever is less electronegative is going to be the positive dipole. And that's what's showing here. So this is polar. The last one is HF is polar. So this is polar. This is nonpolar. And this is nonpolar. And the reason, once again, no difference in electronegativity. There's other ways to make a nonpolar, which we'll get into. So polar molecule is when there is an equal sharing of electrons between the elements bonded together, which I just showed you. Nonpolar is when you have equal distribution of electrons, or somehow we have what's called symmetry, and we'll talk about what that is in a minute. So we'll come back to that idea. All right, so dipole-dipole. Give most electron element a negative dipole with an arrow pointing to it, and give least electronegative a positive dipole. Dipoles canceling means the molecule is nonpolar. So what the heck does that even mean? Well, this is what it means. So let's say we have CO2. Now, when you draw the arrows for this, you know that O is more electronegative, right? For both ends. Do you see how they're equally pulling? Because they're both the same element. So they're going to pull these electrons equally between them. Because they pull equally, you have what's called a nonpolar situation. They're going to cancel each other's effect out. So this molecule is nonpolar. And that's because it's symmetrical. What symmetrical means, the elements on the outside are exactly opposite each other, can cancel each other out. So whenever that's potentially there, you have a nonpolar molecule. Polar, on the other hand, means dipoles don't cancel. So when would that happen? Well, let's say we do an H3. You see how here the dipole goes this way, and it goes this way. So these two can cancel each other out, right? But what's going to cancel this one out? Nothing. So because it's not symmetrical, meaning there's nothing to cancel out this H, we have a polar molecule. So when they can cancel each other out, nonpolar. When they can't, it's polar. So here is when the molecule is polar. So it's a shortcut. So if you memorize these, this will make your life a lot easier. Anytime there's a lone pair off the central atom, you can call it polar. Just call it polar and move on with your life. That's it. Anytime. All you're looking for is a lone pair off the middle. There is an exception to this, but we're not going to deal with that right now. And it's when you have two lone pairs and it's a specific shape. We're not going to deal with that. For our purposes right now, anytime you see a lone pair, polar. End of story. Two different elements on opposite sides of each other. So if I have, like, let's say S, C, and N, S and N can't cancel each other out because they have different electronegativity. So this would be polar. You can't cancel them out. That has to be two different elements for them to cancel out. So keep that in mind. The only exception is CNH. When CNH is involved, it is always nonpolar. So I could have this, huge structure, all these H's floating around. And every time you only see CNH, any molecule with CNH only, you're always going to call them nonpolar. And for those wondering why, because electronegativities are so close together that we say this negligible, so we call it nonpolar. So if you see CNH anytime, we can call it nonpolar. Any other situation where it's two different elements, it's a polar bond and a polar molecule typically. All right, molecule is nonpolar when the element is bonded to itself, I2Cl2, because of similar electronegativities. Resonance structures, remember those ones where you get to choose where the double bond goes? Whenever you have a resonance structure, it is always going to be nonpolar. Compounds involving CNH, which we just mentioned. So if it's CNH only, nonpolar, but you put any other element, Br, O, F, I don't care what it is, don't care how many of them there are, the molecule becomes polar automatically. So if it's CNH only, nonpolar, but any other element added to that besides CNH, you have a polar molecule. Molecule symmetrical, so that's what this is. Remember the CO2 molecule, the polarities cancel out, so you're nonpolar. So these are the situations nonpolar. So what's the most important shortcut in all this? Well, there's two really. One, anytime you have a lone pair off the middle, it's polar. That's a very important shortcut. And second, if it's CNH only, it's nonpolar. That'll prevent you having to draw huge molecules that have a lot of CNHs because you will know it's nonpolar without even drawing it. All right, so let's try some of these. See if they're polar or nonpolar. So CO, 1, 2, 3, O, polar. Y, two different elements. There's nothing to cancel out the O on the other side, or that's automatic. CO2, well, we already know this because we've drawn it or seen it drawn. Remember, symmetrical, cancel each other out. So this is going to be nonpolar. NH3, we saw this before as well. And remember, the problem with this is that lone pair off the middle, polar, don't even have to sit there and do anything else. We know automatically. CCl4, put all your atoms down, count your correct number of valence electrons. Voila, symmetrical. Cancels out. All electronegativities cancel out, so this is going to be nonpolar. All right, Nondispersion forces. Remember, everything has this. The only thing you need to really know about Nondispersion forces, besides the fact everything has it, the bigger it is, the stronger the LDF is. So if you look at this chart, see how as the size goes up, so does the boiling point. Boiling point is the energy you need to make something become liquid and gas, right? So the more strongly the molecules attract each other, the more energy you have to put in to break those interactions and boil. So in the case of size, as you get bigger, you have a higher boiling point, and these are all nonpolar. Anything that's only nonpolar is going to be LDF only. So these are all nonpolar molecules. These all have LDF forces. So LDF, 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 whatever. So you're only looking at LDF. And in case of LDF, the bigger it is, the higher the boiling point, because it's stronger. The force is stronger. So bigger molecules have stronger LDFs than weaker ones. And for those wondering, how do Nondispersion forces even form? Okay, here's how. Two elements are just minding their own business, doing nothing. For whatever strange reason, for a nanosecond, all the electrons on one element end up on the same side. That's what this is showing you. So you have what's called a temporary dipole. So let's say this had 2 electrons. Both these electrons are on the same side. There's no electrons on this side. So this end is going to be negative because that's where the lone pairs are. This side's going to be positive because there's nothing there. So as a result of this, you have a temporary dipole. Now this molecule gets near another molecule and it causes it to do the same thing. It causes the electrons that are hanging out on this side to all come on this side because they want to attract to this positive dipole. And that's what's going on. So now there's an opposite attraction between them. This one that was forced to form a dipole is called an induced dipole. Long story short, now these are both temporarily dipoles. They're not permanent dipoles. They're not completely polar all the time, but just temporarily. And now they can attract each other. And that's what Nondispersion force is. Temporary attraction between 2 atoms or 2 molecules because of the fact that you have these temporary dipoles popping up. And everything has it, everything. And the bigger it is, the more potential for this to happen. Other things that affect Nondispersion forces, the higher the surface area. So the more exposure there is, see how this is more exposure than this, which is compact, it's got little elements hiding, the stronger the LDF. Long, skinny molecules tend to have stronger dispersion force than short, fat ones. So that's why this one has stronger LDFs than this one. All right, IMFs and change of state, just so you're aware, when you're melting something, you're weakening IMFs, which allows them to move more, and that's why they melt. So remember, when you're in solid, the atoms are really tightly packed together, right? When you're melting, you're putting energy into this and you're weakening this interaction, and now they're able to move a little bit more, and that's what causes melting because you're going from a solid to a liquid. Condensation, you're going from a gas to a liquid, and for this one, what happens, you have gases all over the place, right? What happens is that you slow these down enough that 2 of them can get near each other and attract each other, and when they attract, they go from a gas to a liquid. Remember, gases are individual molecules. Liquids are combinations of 2 that are attracted to each other to a little bit, right? So when you're condensing, you're actually getting them close enough by losing energy, making them move slower. They can attract each other, and now they can become a liquid. Freezing, as liquid molecules lose energy, they begin to attract each other due to their IMFs. Basically, what you're doing is that the liquid, remember the solid has a little bit, it has almost no distance. Liquid has a little bit of distance between them. You're making them move slower and slower. So now they're attracting each other more. And now they're almost motionless and they become a solid. And that is a loss of energy for it. These are all IMS related. Everything with physical changes, these are all physical changes, by the way, are going to involve intermolecular forces. Boiling, as the molecules in a liquid get more energy, they begin to break the IMS between them and change to gas. So here's a liquid, there's a little attraction between this liquid and this liquid. This breaks because you're putting enough energy in to make them move too fast past each other. So they break and become a gas. So the only time you break IMFs is when you go from a liquid to gas. When you're going from solid to liquid, you're just weakening the IMFs. All right, so let's determine what the IMFs each of the following are. So let's practice this concept a little bit to see if we understand it or not. So for CCl4CH4, I don't need to draw this because CNH I know is nonpolar. And the beautiful thing about nonpolar molecules is they're only going to have LDF typically. There's only one example I could think of where it doesn't, but we'll deal with that another time. For CCl4, we know symmetrical because carbon can only have 4 around, and we drew this earlier too. So this is going to be nonpolar as well, it's just LDF. So they both have LDF. The question is which one's going to have a higher melting point? Well, which one's bigger? Chlorine is a lot bigger than hydrogen, so this is going to have a higher melting point. All right, next one, CH3OH and C2H6. So we have to draw this one out because it's a little bit tougher. So I'm going to put C, H, 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 O, H, and 2 lone pairs, and we're good to go. And then for C2H6, I'm not going to draw it, but well, I'm going to draw it. Forget it. I'll draw it so you can see how to do it. So when you have multiple carbons, they do this little thing, the chain structure. And what you do, you're going to distribute the hydrogens evenly between the 2. So there's 6 total, so I'm going to give each of them 3. If there were 4 total, I'd give each of them 2. That's just the way it works. If they have 2 total, 1 each. You're not going to see an odd number. So for this situation, this is what it looks like for C2H6. Well, without even drawing it, I knew this was going to be nonpolar, right? Because CNH only is always nonpolar, which means it's LDF. because everything has LDF and nonpolar molecules, that's all they have. For this one, LDF is still there, that's guaranteed, because that's always there. But we also have a polar molecule, because remember, as I told you earlier, if it's anything besides C and H, it's automatically dipole-dipole. So it's polar, dipole-dipole. And you could see that because the carbon on this side has a hydrogen, on the other side has an O, those two can't cancel each other out. So that's why it's polar, in case you're wondering. And it has hydrogen bonding too, because look, H is bond to O. It's one of the fun molecules. So it has all three. So you notice this only has LDF, this has all three. The strongest for this is one of the strongest forces available. So this is going to definitely have the higher melting point, because you have to put enough energy to break that IMF, and that IMF is extremely strong. All right, H2 or SO2, we're going to draw it out. And SO2 looks like this. You notice how I draw it is the same way I'm teaching you guys how to draw it. Erase and move. Okay, it's a resonance structure. So remember, resonance structure is supposed to be nonpolar, but lone pair trumps everything. Once you have a lone pair, it's game over. It's dipole-dipole. Have a nice day. So this is dipole-dipole. You also have Nondispersion forces because everything has it. But the strongest force is going to be dipole-dipole in this one. For this one, we have Nondispersion, automatic, right? Dipole-dipole. And you have H bonding. So this is stronger than dipole-dipole. So because this has a stronger IMF than this does, this is going to have a higher melting point. HF or HCl. Here's HF. Here's HCl. So they look similar, right? Except this has a F, this is a Cl. Something else more important though, this one just has LDF, guaranteed. Dipole-dipole, because it's two different elements, that's going to be standard. Here, HF, Nondispersion, definitely. Dipole-dipole, definitely. But guess what? Also has H bonding because it's one of the fun molecules. So this is going to have stronger IMF, so this is going to be the winner of the contest. So those are the intermolecular forces and how they're applied.